Welcome to today's walkthrough of LeetCode problem number 921, minimum add to make parentheses valid. In this session, we'll explore how to determine the minimum number of parentheses that must be added to make a given string valid. We'll break down the problem, discuss different approaches, and provide insights into the optimal solution. Let's get started. In this problem, you are given a string S that consists of only the characters, and, representing opening and closing parentheses. Your task is to determine the minimum number of parentheses that need to be added to make the string valid. A valid string is one where every opening parenthesis has a matching closing parenthesis, and all parentheses are closed in the correct order. For instance, a string like is valid because the opening parenthesis is properly closed, but a string like is not valid because it has unmatched opening parentheses. Similarly, a string like is invalid because the order of the parentheses is incorrect. The goal is to calculate the minimum additions required to fix the input string and make it valid. The input to the problem is a string S with a length between 1 and 10,000 characters, and it consists only of the characters, and the output is an integer that represents the minimum number of parentheses that need to be added to make the string valid. For example, consider the string S equals. Here, there is one unmatched closing parenthesis, so we only need to add one opening parenthesis at the start to make the string valid. Therefore, the output is 1. For the string S equals, the explanation is straightforward. There is one unbalanced closing parenthesis, which does not have a corresponding opening parenthesis. To fix this, we can add a single opening parenthesis at the start of the string, making it. Since only one addition is needed, the output is 1. Now, let's look at another example. For the input S equals, there are two unbalanced opening parentheses that do not have matching closing parentheses. In this case, we need to add two closing parentheses at the end of the string to make it valid. For the string S equals, adding two closing parentheses results in the valid string. Since two additions are required, the output is 2. Now, consider the example S equals. Here, the string is already valid because the opening parenthesis has a corresponding closing parenthesis, and they are in the correct order. No additions are needed, so the output is 0. This highlights that if the input string is already valid, the result will always be 0. Next, let's look at the example S equals. This string has one unmatched closing parenthesis at the start and one unmatched opening parenthesis at the end. To make the string valid, we need to add one opening parenthesis at the start and one closing parenthesis at the end. This transforms the string into. Since two additions are required, the output is 2. These examples show how the problem handles different kinds of invalid strings and the changes needed to make them valid. The problem comes with some constraints and edge cases to consider. The length of the string S is guaranteed to be between 1 and 10,000 characters, and the string only contains and. The solution must be efficient, ideally with a time complexity of O(n), where n is the length of the string. For edge cases, if the string contains only opening parentheses, such as S equals, the output will be the length of the string, since all opening parentheses need to be closed. Similarly, if the string contains only closing parentheses, the output will also be the length of the string, as each closing parenthesis needs an opening one. If the string alternates valid pairs, like S equals, or has nested valid pairs, like S equals, the output will be 0 because the strings are already valid. These constraints and examples guide the development of an optimal solution to the problem. To solve the problem of determining the minimum number of parentheses needed to make a string valid, we need to focus on the balance of opening and closing parentheses. A valid string ensures that every opening parenthesis has a matching closing one, and they are properly nested. Several approaches can be considered. One straightforward idea is a brute force method, where we manually balance parentheses by making two passes through the string. The first pass counts unmatched opening parentheses, while the second pass counts unmatched closing ones. Adding these values together gives us the total additions required. While this approach is simple and intuitive, it's not the most efficient or elegant solution, so we'll explore alternatives next. A more structured approach involves tracking unmatched parentheses with a counter. As we iterate through the string, we increment the counter for each opening parenthesis and decrement it for each closing one. If the counter goes negative, it indicates an unmatched closing parenthesis, which we need to address by resetting the counter. This method has a time complexity of O(n), as the string is traversed twice, and a space complexity of O(1), since no additional data structures are used. However, while easy to implement, this solution has trade-offs. Requiring 2 iterations makes it less efficient than other methods, and it lacks the elegance of more streamlined approaches. Another alternative worth considering is the stack-based approach. Using a stack, we can simulate the process of matching parentheses. Each opening parenthesis is pushed onto the stack, and every closing parenthesis pops the top of the stack if it's not empty. If the stack is empty when a closing parenthesis is encountered, it indicates an unmatched closing parenthesis, which we track with a separate counter. At the end, the stack size represents the unmatched opening parentheses, and we combine this with the unmatched closing count to get the total additions. This method requires only a single pass, giving it an O(n) time complexity, but it also introduces an O(n) space requirement due to the stack. While it's a cleaner approach than brute force, the extra space usage is unnecessary, as we only care about counts, not the positions of unmatched parentheses. This leads to an optimized approach. To maximize efficiency, we can eliminate the stack entirely and use 2 counters to track unmatched parentheses in a single pass. The first counter, close_needed, tracks unmatched closing parentheses. It is increment for each opening parenthesis and decrement for each closing one. If it becomes negative, this indicates an unmatched closing parenthesis, so we increment a second counter, open_needed, to record it and reset close_needed to 0. By the end of the traversal, the total additions needed are simply the sum of open_needed and close_needed. This approach achieves O(n) time complexity with O(1) space, as it avoids any extra data structures. It is both elegant and efficient, making it a strong candidate for the optimal solution. The chosen strategy for this problem is the optimized greedy approach. By maintaining 2 counters, open_needed and close_needed, we streamline the process while minimizing both time and space complexity. This method is intuitive, avoids the overhead of a stack, and ensures a single efficient pass through the string. Its O(n) time complexity and O(1) space complexity make it the ideal solution. Compared to the brute force approach, the greedy method reduces the number of iterations and simplifies the logic. Compared to the stack-based approach, it avoids unnecessary memory usage. This balance of simplicity, efficiency, and elegance underscores why the greedy approach is the best choice for solving this problem. In this problem, our goal is to determine the minimum number of parentheses that need to be added to a given string to make it valid. A valid parentheses string has 2 key properties: every opening parenthesis must have a corresponding closing parenthesis, and the parentheses must be correctly nested. To solve this problem, we can use a greedy approach that relies on 2 counters to track unmatched parentheses. First, we initialize these counters. The open_count tracks unmatched opening parentheses, while the close_count tracks unmatched closing parentheses. Both are set to 0 at the start. These counters will help us efficiently track the number of parentheses we need to add as we process the string. Next, we traverse the string character by character. If we encounter an opening parenthesis, we increase the open_count because it represents an unmatched opening parenthesis that we may need to pair later. When we encounter a closing parenthesis, we check if there's an unmatched opening parenthesis available. If so, we decrease open_count, effectively matching the opening and closing pair. However, if there's no unmatched opening parenthesis available, we increase close_count, as this closing parenthesis is currently unmatched and will need a corresponding opening parenthesis. After traversing the entire string, we calculate the total number of parentheses needed to make the string valid by adding open_count and close_count. The unmatched opening parentheses will require closing parentheses, and the unmatched closing parentheses will require opening ones. This approach works effectively because of a key insight: by decrementing open_count whenever we encounter a closing parenthesis, we greedily match as many pairs as possible during the traversal. This ensures we don't overcount unmatched parentheses. The algorithm is highly efficient since it processes the string in a single pass, making the time complexity O(n), where n is the length of the string. Additionally, it uses only 2 integer counters, meaning the space complexity is O(1). Unlike alternative solutions that may use stacks, this approach is both simpler and more memory efficient, as the counters alone are sufficient to determine the number of unmatched parentheses. To better understand the algorithm, let's look at an example. Consider the input string. Initially, both open_count and close_count are set to 0. As we traverse the string, the first character is an opening parenthesis, so we increment open_count to 1. The second character is a closing parenthesis, which matches with the previously unmatched opening parenthesis, so we decrement open_count back to 0. The third character is another closing parenthesis, but there are no unmatched opening parentheses left, so we increment close_count to 1. Finally, the fourth character is an opening parenthesis, so we increment open_count to 1. After traversing the string, the total number of parentheses needed is open_count plus close_count, which is 1 plus 1, resulting in an output of 2. Now let's consider some edge cases. For an empty string, both counters remain 0, so the output is 0. If the string consists entirely of opening parentheses, such as only open_count increments, and the result is equal to the length of the string. Similarly, if the string consists entirely of closing parentheses, such as only close_count increments, and the result is also equal to the string length. The time complexity of this solution is O(n), due to the single traversal of the string, and the space complexity is O(1), because only 2 counters are used. This greedy approach eliminates the need for a stack, reducing memory usage and computational overhead. By directly calculating unmatched parentheses during traversal, we avoid any additional processing, making the solution both elegant and efficient. The solution to LeetCode problem number 921, minimum add to make parentheses valid, is implemented using a greedy approach with 2 counters to track unmatched parentheses. ###explanation. 1. Initialization. 2 counters, open_needed and close_needed, are initialized to 0. These track the number of unmatched opening and closing parentheses, respectively. 2. Iterating through the string. For each character in the string S, we check if it is an opening parenthesis or a closing parenthesis. If the character is, it means we require a matching closing parenthesis later in the string, so we increment open_needed. If the character is, if there are unmatched opening parentheses, open_needed 0, we decrement open_needed because this can match with a previous. If there are no unmatched opening parentheses, we increment close_needed, as this closing parenthesis is unmatched. 3. Final calculation. At the end of the loop, the total number of additions needed to make the string valid is the sum of open_needed and close_needed. Open_needed accounts for unmatched, and close_needed accounts for unmatched. 4. Complexity. Time complexity, O(n), where n is the length of the string S, because we traverse the string once. Space complexity, O(1), as we use only 2 integer variables for tracking. This approach is efficient and handles all edge cases, including an empty string, S equals, which returns 0, and strings with no parentheses, e.g., S equals ABC, which also returns 0. The greedy matching ensures that the solution is optimal and minimal additions are computed. This is the Java implementation of LeetCode problem number 921, minimum add to make parentheses valid. It mirrors the Python logic by iterating through the string, counting unmatched opening and closing parentheses using 2 counters. The total additions required are the sum of these counters. Key differences include Java's explicit type declarations and the use of the tchar array method for string traversal. To solve this problem, we need to identify how many parentheses are unmatched in the given string. Let's start with the first example, where the input is S equals. Initially, we set 2 counters, open_needed to track unmatched opening parentheses and close_needed to track unmatched closing parentheses. Both are set to 0. Now, as we process the first character, which is, we see that it's an opening parenthesis. This means we need to increase open_needed by 1, as it represents one unmatched opening parenthesis. At this point, the state is open_needed equals 1 and close_needed equals 0. Next, we process the second character, which is. Since there is an unmatched, we decrease open_needed by 1, effectively matching the opening parenthesis. Now the state becomes open underscore needed equals 0 and close underscore needed equals 0. For the third character, another, there is no unmatched available to pair it with, so we increase close underscore needed by 1 to account for this unmatched closing parenthesis. The final state here is open underscore needed equals 0 and close underscore needed equals 1. In the final state of this example, we calculate the total number of unmatched parentheses by adding open underscore needed and close underscore needed, which gives us 0 plus 1 equals 1. Thus, the output for this input is 1. Now, let's look at the second example, where the input is s equals. Again, we initialize both open underscore needed and close underscore needed to 0. The first character is, so we increase open underscore needed by 1, representing one unmatched opening parenthesis. The state becomes open underscore needed equals 1 and close underscore needed equals 0. The second character is another, so we increase open underscore needed again, bringing it to 2. At this stage, the state is open underscore needed equals 2 and close underscore needed equals 0. In the final state of this second example, we calculate the total unmatched parentheses. Since there are two unmatched opening parentheses and no unmatched closing parentheses, the total is open underscore needed plus close underscore needed equals 2 plus 0 equals 2. Therefore, the output for this input is 2. Now, let's move on to the third example, where the input is s equals. Once again, we start with open underscore needed equals 0 and close underscore needed equals 0. The first character is, so we increase open underscore needed to 1. The state becomes open underscore needed equals 1 and close underscore needed equals 0. The second character is, and since there's an unmatched, we decrease open underscore needed to 0, effectively matching the pair. Now the state is open underscore needed equals 0 and close underscore needed equals 0. For the third character, there is no unmatched available, so we increase close underscore needed to 1. The state becomes open underscore needed equals 0 and close underscore needed equals 1. Processing the fourth character, another, we again find no unmatched available, so we increase close underscore needed to 2. The state is now open underscore needed equals 0 and close underscore needed equals 2. Next is the fifth character, which increases open underscore needed to 1, resulting in open underscore needed equals 1 and close underscore needed equals 2. The sixth and final character is another, so we increase open underscore needed again, bringing it to 2. The final state is open underscore needed equals 2 and close underscore needed equals 2. Adding these values gives us the total unmatched parentheses, open underscore needed plus close underscore needed equals 2 plus 2 equals 4. Thus, the output for this input is 4. The time complexity of the solution is O(n), where n represents the length of the input string. This efficiency comes from the fact that the algorithm processes each character in the string exactly once. To break it down, the loop iterates through each character in the input, which takes O(n) time. Within the loop, we perform constant time operations such as checking if a character is an opening or closing parenthesis and updating counters. These operations are executed for every character, so their contribution is proportional to n. When you combine the iteration and these constant time updates, the overall time complexity remains O(n). The space complexity of this solution is O(1), meaning it uses a constant amount of additional memory regardless of the size of the input string. This is because the algorithm relies on just two integer variables, open underscore needed and close underscore needed, to keep track of unmatched parentheses. These variables require a fixed amount of space. Furthermore, the input string is processed directly without being modified or duplicated, so no extra storage is required. Since no additional data structures are used that grow with the input size, the overall space usage remains constant, resulting in O(1) space complexity. A naive approach to solving this problem might involve using a stack to keep track of unmatched opening parentheses. For each closing parenthesis, the algorithm would attempt to pop from the stack, and unmatched closing parentheses would be counted separately. While this approach also has a time complexity of O(n), its space complexity is O(n), because, in the worst case, the stack could grow to store all unmatched opening parentheses. The optimized approach presented here eliminates the need for a stack by using two counters to track unmatched parentheses. This reduces the space complexity from O(n) to O(1), while still maintaining the same O(n) time complexity. In terms of the best, average, and worst case scenarios, the algorithm consistently achieves O(n) time and O(1) space complexity. In the best case, where the input string is already valid, such as, the algorithm processes each character once, resulting in O(n) time. For the average case, with a random string of parentheses, the algorithm still processes all characters linearly, maintaining the same efficiency. In the worst case, where the string is entirely unmatched, such as, the algorithm still processes each character in a single pass. Mathematically, the time complexity is derived from the single iteration over the input, which takes O(n), and the constant time operations within the loop, which are O(1). Combining these gives O(n) overall. Similarly, the space complexity remains O(1), because the algorithm uses only two fixed integer variables regardless of input size, with no additional memory allocation. One of the most common mistakes when solving this problem is confusing validity with balance. It's important to remember that just because a string has an equal number of opening and closing parentheses, it doesn't mean the sequence is valid. For example, the string may be balanced in count, but the order makes it invalid. Always ensure you check the sequence, not just the number of parentheses. Another frequent pitfall is using nested loops to check and fix validity. This approach leads to a time complexity of O(n squared, which is unnecessary since the problem can be solved in linear time with just a single pass. Additionally, when using counters to track unmatched parentheses, forgetting to reset the counter properly when it goes negative can lead to errors, particularly when there are extra closing parentheses. Make sure these mismatches are handled and recorded separately. Beginners also sometimes overcomplicate the solution by simulating a stack explicitly, even though simple counters can achieve the same result with less space. Finally, it's crucial to account for edge cases like an empty string, a string with only opening parentheses, or one with only closing parentheses. Overlooking these can easily cause your solution to fail in specific scenarios. This problem is a great opportunity to demonstrate your understanding of simulating stack-like behavior with minimal space. In interviews, a common follow-up question might involve asking you to optimize your solution further or explain why a counter-based approach is sufficient. Many parentheses problems share a similar foundation, relying on the stack or counter technique. Being able to recognize when a stack is truly necessary versus when counters suffice is a valuable skill. Interviewers often appreciate when candidates can discuss the trade-offs between different approaches. For this problem, the counter-based method is typically preferred due to its simplicity and O(1) space complexity. Another key expectation in interviews is handling edge cases effectively. Scenarios like strings with all opening or all closing parentheses are often tested, so ensure your logic is robust enough to address them. Additionally, it's worth noting how this problem connects to other related challenges. For instance, LeetCode 20 involves validating a parentheses string using a stack, while LeetCode 1249 focuses on removing invalid parentheses to make a string valid. LeetCode 678 introduces the added complexity of wildcard characters, and LeetCode 856 deals with scoring a valid parentheses string based on its structure. Familiarity with these variations can help you recognize patterns and strengthen your understanding of this topic. There are multiple approaches you can take to solve this problem, each with its own advantages and trade-offs. One option is the stack-based approach. Here, you push unmatched opening parentheses onto the stack and pop them for closing parentheses. At the end of the iteration, the size of the stack combined with any unmatched closing parentheses gives you the result. While this method is clear and intuitive, it uses O(n) space, which may not be ideal. A more optimal solution is the counter-based approach. Using two counters, one for unmatched opening parentheses and another for unmatched closing parentheses, you can track mismatches as you iterate through the string. This method achieves the same result in O(n) time but with O(1) space, making it the preferred choice in interviews. Another alternative is the greedy approach, which dynamically tracks balance and minimizes mismatches as you iterate. While it's conceptually similar to the counter-based method, the greedy approach emphasizes making adjustments in real time. In terms of trade-offs, stack-based solutions are often easier for beginners to grasp, but counter-based methods are more efficient and simpler in terms of space usage, making them a stronger choice for scenarios where performance matters. Great job making it through the problem. To summarize, we discussed how to calculate the minimum additions needed to make a parentheses string valid. We reviewed the optimal approach, its complexity, and key concepts like balance tracking. Keep practicing similar problems to sharpen your skills. Thanks for watching, and don't forget to like and subscribe for more content. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!